You're listening to the Thesis Review podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to diving into the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and how the field itself has evolved since their PhD days. My guest today is Gus Xia, who is now an assistant professor at New York University Shanghai. Gus is an expert in the field of machine learning for music, with the goal of building intelligent systems that understand and extend musical creativity and expression. He did his PhD at Carnegie Mellon, advised by Roger Dannenberg, and graduating in 2016. He then went on to do a postdoc at Dartmouth University, and then became an assistant professor at New York University's Shanghai campus, where he is now building and leading the Music X lab. His PhD thesis is titled Expressive Collaborative Music Performance via Machine Learning, and deals with using machine learning for automatic accompaniment, improvisation, and for building robots that have facial and gestural expressions and reactions to the music that they take part in. It was a fascinating conversation, covering the specific work in the thesis, music and AI in general, and where he has taken his work on machine learning for music since. There are links to his thesis and the papers that we mentioned in the show notes. I also recommend checking out Gus's website, which has clips of the music and the robots that we discuss. And now, here's Gus Xia with Expressive Collaborative Music Performance via Machine Learning on the Thesis Review. Well, we could start with an easy question. So you're kind of in the unique position of being both a musician as well as a researcher. So do you see similarities between composing or performing music and writing a scientific paper?
At the beginning, it's completely different. And I was at the first place a professional performer. So when I stepped into the field of science, well, of course I studied computer science sort of in my undergrad, but it's far from a very, formal training. So when I was doing my PhD, I certainly feel the conflict. The conflict, not only in the way that how people, deliver their result, but also how people think. Well, there's two different ways of thinking.
Yeah, I see.
So let me try to summarize. So, but now I'm just talking to for the shallow part. So for the shallow part, science and engineering, let me just talk about computer science because I can't speak for other views. So computer science guys, we think of representation first, and then the behavior is just normal. For example, we talk about data structure and algorithm, right? We first have the data structure and then we talk about algorithm, because if we have the data structure, the algorithm should be obvious. And so we have the foundation. We rarely, talk about an algorithm and then try to reverse engineer the data structure. But for performers think of the problem in a completely different way. So when we learn how to perform music, we think of behavior first. So if you do such and such and such, you will have, you can successfully play an A. It's through the practice of behavior, you gradually enhance the idea of representation. So it conflicts. And when I think about the CS problem, my advisor, constantly try to correct me that the order of my logic is reversed, is wrong. Yeah.
Yeah, I see. That's interesting. It seems like potentially with machine learning, you might first think about what type of behavior you want, and then think about how to develop the algorithm. Do you think maybe machine learning is a bit different than like this computer science view that you described?
Yes, especially deep learning. especially
Mm-hmm.
deeper. If we want to, um, it seems the current trend is we're trying to build a perception system and build on this, the so-called system one perception, how we can derive the system two logic or whatever we call it, symbolic manipulation.
Yeah,
So
I see.
if the system two could naturally derive from system one, well, I don't know how to do it so far, or it's an open problem. Um, if we can do that, then it's, first have the behavior and then representation. Maybe that's, yeah, it's interesting.
Mm-hmm.
So that's why
Yeah,
I'm
I
saying
see.
that at a shallow part, it seems completely different, but underneath, uh, underneath, actually the order doesn't matter that much. Is the truth that the two systems should work together, and it forms a loop. Once it forms a loop, the order doesn't matter, right?
Right, I see. So they might be
Yeah,
aiming for similar things, just going at it in different directions.
yeah.
Yeah. Yeah, maybe let's go back then. So what was your background in music before your PhD?
I was a well-trained Chinese flute and vertical flute performer.
Hmm.
Um, yeah, for more than 10 years. I also play a little bit piano, saxophone, but that's kind of amateur level. I actually once won the first place of the so-called National Instrument Proficiency Evaluation. Yeah,
Mm.
I was the number one out of more than 3,000 competitors.
Well,
Yeah, yeah.
when did you decide to do a PhD and specifically in the computer science?
Um, that was in my senior year. Uh, my undergrad major was information science, and I did a minor in psychology. So
Mhm.
my undergrad years was mostly devoted to the Chinese Music Institute. So we have a student group organization, and I was a soloist and leader for several years there. So I had a lot of fun, and my major is okay, but when I was a junior, senior, I was thinking that how I could combine my major and minor in psychology and my passion of music. So I talked
Yeah,
to
yeah.
a lot of professors actually, and none of them gave me a very you know um, inspiring answer until I met
Mhm.
my music teacher. He had a background in new media, and he told me, "Oh, it's easy. You should just Google for computer music, and maybe Carnegie Mellon's computer music group or MIT's Media Lab will give you a lot of inspiration." So I go back and did my homework and decide, oh, that's the area that I should pursue.
I see. Yeah, so that's interesting. So going into the PhD, you kind of had this vision of combining music with computer science, or at that time, did you already think about machine learning specifically or artificial intelligence?
No, I didn't even know the words actually. And funny enough that um, that time I was at Beijing, and I was trying to do a PhD with um, Roger Dannenberg, a professor in Carnegie Mellon. And one day, Adam Blum from CMU came to Tsinghua University, which is just beside Beida, where I did my undergrad. And I have no idea who is Adam Blum and sorry, Abram Blum, and I just shoot Roger an email saying that can I meet with this guy and chat with him? It's just very casual, and I believe it's that kind of informal interview that helped me a lot. Yeah.
I see. Before we talk about what you did during your PhD, let's take a step back and just talk about this music and AI in general. So
Mhm.
what are some of the, just like for people who haven't heard of this subfield before, what are some of the different problems that people look at in music and machine learning?
Well, speaking of music AI, so basically, all the problems come from music domain, right? So
Mm,
we have something that we want to do in music, but the traditional technology cannot do it. For
mhm,
example, music recommendation, right? So basically, we are trying to um, leverage the technology to help people better appreciate music, perform music, and compose music. So these three, you know, appreciation, performance, and composition are the three main activity in music. So we're trying to, use AI to better do it. Yeah.
I see. So I guess the one that's less well defined for me is the appreciation. So what are some examples of that?
Oh, it's so far it's just a music recommendation system. You
Oh, I
listen
see.
to music and I want to recommend some similar song. Um, of course, that's very shallow, and I guess I believe people in the future want to do that. You know, um, where does the style of this particular song come from? So
Hmm.
what is the so-called ancestors of this song? And I believe some data mining algorithm can do it in the future. Yeah, but so far it's still collaborative filtering based algorithm that yeah, it's kind of Amazon stuff. You buy A and probably you want to buy B. Yeah. So also in the first place, genre classification is probably one of the earliest machine learning algorithm that's applied to music. Yeah.
I see.
Yeah.
So then your thesis, the title is Expressive Collaborative Music Performance via Machine Learning. You said at the beginning of the PhD you didn't know exactly what problem you were going to work on. At what stage did this kind of begin to take shape?
Um, it may be a little special for my case because I get this idea um, sort of in my second year, so very
Mm,
early. Um, so as I said, when I did my PhD in 2010, uh, most of the field are doing um, genre classification, uh, beat detection, tempo estimation, source separation, this kind of thing. So it's we call it
mhm,
machine listening or music information retrieval. So people are trying to use algorithms to analyze the music better.
mm,
Okay, and I'm more interested in the creation part.
mhm.
And because I'm a well-trained performer and I feel very lonely at Pittsburgh because I don't have a band to do accompaniment for me. So I want to create an agent that can play along with me. Plus,
I see.
plus my advisor is one of the inventors or the inventor of the earliest automatic accompaniment algorithm. So it naturally comes to me that whether I can turn the rule-based accompaniment algorithm into a learning-based one. You know,
Mm,
learning-based means learn from your rehearsal and learn the performance style because that's what I do all days. In rehearsal before we go on stage. It seems everything is improvisational. It seems everyone look at each other and get a hint. But the story is not. Everything on the stage pretty much 90% is rehearsed. We know when
mhm,
to look at each other. We know when to speed up and when to slow down. And it's not a template. It's kind of a time series regression problem to me. If you speed up 30%, then later on you should slow down 20%. We kind of have learned this complex associations, this correspondence through rehearsals again and again. So I want to build an algorithm. Yeah. So I get this initial idea very early. I mean, even the first year. But first year, I'm taking courses, so very busy. And starting from my second year, I was chatting to my advisor whether I could pursue this direction. Yeah.
Yeah, I see. So that definitely, so this notion of accompaniment, that corresponds to this word collaborative. What about the word expressive? So what's the difference between just performing and having an expressive performance?
Uh, yeah. So actually, by performance, we mean that you wanna be expressive. Um,
Hmm.
that's on top of the static score.
I see.
So in music we have three levels of representation, so-called. So the very abstract highest level representation is the it's called sheet music or symbolic stuff, right? The score, the
Hmm.
Western sheet music we read. So there we can only have the pitch and durations and the keys, and that's it. And then we have the second level is performance. So at the performance level, we can add expressive timing and dynamics, so loud or soft, yeah. So fast or slow. So of course, in the score, you can also label it, but it's in a symbolic way and not very detailed. Yeah. And
I
at the
see.
bottom level, we have sound, concrete sound, so audio or spectrogram. So my PhD thesis was kind of trying to working on the second level, the middle level of representation. So yeah.
Yeah, so I guess if I understand, then the composer will create a score, but then you still have to put the score into a performance, and the kind of mapping from score to performance isn't perfect. I mean, that's why it's so difficult to be a good performer, because you have to
Yes,
convert this musical score into some expressive performance.
yes,
Yeah, I
absolutely.
see.
And it's kind of a optimization problem. And if we just want to try to solve the mapping from score to performance, obviously there are many possible solutions, right? Or I
Hmm.
should say there are many local optimal.
Yeah.
Because two different master performers could play the same piece dramatically different, and they are all very very good. So then it turns to be a ill-defined problem. So how can I well define that my performance is the performance I generated is good? So the
Hmm.
solution is add the constraint of collaboration. So I'm not trying
Mm.
to optimize the mapping just from score to a performance, but also under the constraint of the solo's performance. And then it becomes a sort of well-formed machine learning problem.
I see. Yeah. Yeah. So then let's talk about. So this is kind of the first major topic, is this accompaniment. Um, so accompaniment, I guess, as we've talked about, you have, I guess, a human playing, and then you
Mhm.
want to have some model, I guess, which you run online as the, like in the ideal case, you have a model that you're running online, and it's going
Mhm.
to change the way that it's playing based on the way that the human is playing.
Yes, yes.
I see. Yeah. Yeah. I was thinking about this. It seems, so I've worked on this dialogue problem in language,
Mhm.
and dialogue is kind of nice because you have one person talk and then the next person talks, and it's kind of this alternating thing. But it
Yeah.
seems like with this accompaniment, it's kind of like both people are speaking at once and you have to make it sound good.
Yes, that's why it's a hard problem that you know all the NLP task, I would say, our purpose is that it's understandable, right? We want it to be understandable. You do not have to completely cheat the human, saying, "Oh, the agent on the other side is a human." We actually do not have to pass the Turing test. That's not our goal. The goal is we can understand, we can use it. But for music, it's kind of, if it doesn't pass that artistic bar, what's the point of doing it?
Yeah, I see.
Yeah,
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 if you make the overall music worse by introducing the machine learning component, then what's the point?
yeah. So in some sense, it's a harder task. Yeah.
Yeah. So then, if you can remember, so the specific, we could talk about maybe how you would approach this problem today, but in the thesis, what was the specific method that you used? Like, what does actual accompaniment mean in the thesis? Like, what are the inputs? What are the outputs?
Oh, it's actually pretty easy. That's very straightforward. The input is
Hmm.
first the score, or at least
Hmm.
the lead sheet um, of a score. Or a lead sheet means um, you at least have the chords labeled with the main melody.
Hmm.
Um, and the second input is solo's performance. Yeah,
I see.
and the
And then
output is
it'll, yeah,
the output is just the accompaniment. And if the score is already given, then it becomes the detailed timing and dynamics of the accompaniment. Every note we can decompose into a note by note decision making process.
I see. So, what does dynamics mean?
Dynamic just I was mainly working on the piano accompaniment. So dynamics means the loudness or the velocity, so-called velocity of how fast you push the key.
I see. Yeah, yeah. And then one thing I thought was interesting is when you were talking about the models in the thesis,
Mm-hmm.
I guess you learned a separate model for each note. It said the
Mm-hmm.
per note models.
Mm-hmm. Mm-hmm. That's the first model. Yeah, that's the first model.
I see. And
Yeah.
then the more complex ones, so like this linear dynamical system,
Yes.
that was that was different.
Oh, yes, that's completely different. I start from the so-called node-specific model, which
Hmm.
only, I have to have 30 or 40 rehearsals because uh, those 40 to 30 to 40 rehearsals was trying to, um, learn the model for each individual node. So I need a lot of rehearsals, a lot of data. Um, and so that's the first model. And then I try to uh, generalize the model, right? Or sorry, I try to build more and more general model, including rhythm specific and eventually the linear dynamic system thing. So for that one, I only need 4 to 8 rehearsals in order to learn a performance style. Yes. Yeah.
Yeah, yeah. Yeah, actually on that note, let's talk about the data. This is something in this deep learning era where we're seeing bigger and bigger data sets, with millions of examples. I thought this
Yeah.
was pretty fascinating that you constructed this data set and it had 189 or 10 pieces and 189 performances, and
Yes.
you were able to learn these models. It seems like that would be
Because
very challenging for, yeah,
I'm not using deep learning models. I'm using
exactly,
linear.
yeah.
That's why that's so far. Um, that's why actually so far I do not have a better solution than LDS for performance problem.
Yeah,
Because in
yeah,
most
that's
deep
really
learning
interesting.
system, let's just do RN or LSTM, they need well 100 performance. 100 rehearsals at least. But who can afford collect that much data?
Mhm.
Uh, so far the best you know um, accompaniment model is still linear.
I see. Yeah, it's really interesting.
Yeah,
I think
I
another
guess transfer learning can work. Yeah, transfer learning would work. We can use a large amount of data, non-collaborative data, so solo data that we have a lot of them, millions of them
yeah,
maybe, to train a pre-train a model and then try to do zero shot future learning for accompaniment. I think that's the future direction, but I'm not working on that now.
Yeah, that would be really interesting because
Yeah,
especially in language, that's becoming the dominant kind of paradigm for these tasks where you have small amounts of data.
yeah.
Yeah. So then another interesting thing that you noted here is with this linear dynamical system, if anyone's reading along, it was called Discovery Number 7, and it said that there's a latent expressive space which explains a significant portion of musical expression, and it's only
Yes.
4 to 7 dimensions.
Yes.
So
Exactly.
my question is like, did this, because I know that nowadays you work on these variational autoencoder models with this latent space. So was this kind of the first finding that made you interested in this type of thing, like finding this lower dimensional representation of the performance?
Exactly. Oh gosh, you are a good, how should I say, detector.
That's why we're doing this podcast to go back and trace the path.
That's amazing. Yes, that's from, but the LDS, the latent space is just SVD. It's linear. But still, for performance, it seems to be okay. So linear system seems to be fine for performance problem. But for composition problem, what I'm working on now, obviously the linear model won't work, and we need more powerful representation learning models, say VAE and all the improvement, disentanglement whatsoever we're working on.
Yeah, I see. So yeah, maybe we'll go on to the next topic, this improvisation, in a second.
Yeah.
Why don't we talk about that existing work that you're doing now on with VAEs and on this latent representation?
Yeah. Actually, it's very similar. I'm just transferring from, generate performance to the creation of composition. It's the same concept, and especially in a sense that I'm not very interested in automated composition. Vanilla, I would say vanilla automated composition. I'm interested in interactive composition and controlled composition. So the sense of human-computer interaction within the AI framework is deeply rooted in my heart. Yeah. So I think any AI algorithm should be able to interact with human input. Yeah. So for my thesis is the performance should be collaborative, should do accompaniment for a human, and now the composition model is the created composition should go along with a well-defined human input. For example, a motive, a chord progression, or some rhythmic patterns, something like this. Yeah.
I see.
Yeah.
And so the idea there is, if I remember correctly, so you learn this latent space, and the goal was to disentangle it to the point where you're able to adjust these different characteristics that you're talking about. Is that, yeah.
Yeah,
So,
because only through disentanglement, well, I should say, through disentanglement, we can improve the interpretability of the model. And only through improving the interpretability of the model that we can turn the model into a controllable interface. Otherwise, all the latent variables, we have no idea what they are, and they will remain a black box. Yeah.
Right. You're just toggling different numbers in a vector.
Yeah,
otherwise.
yeah.
Yeah. Are you kind of like, where is this problem at? Like, how difficult is this problem? Are you satisfied with the amount that you're able to control these latent characteristics, or do you think there's more work to be done here?
Oh, there's a lot of work to be done here, and we are just getting started, I believe.
Hmm.
So I start from two measure, so that's 8 beats for 4/4 composition. We start from the melody, 8 beats melody, and that's the deep music analogy paper. And now we can do 8 beats piano accompaniment. So now it's polyphony. And currently, what we are trying to learn is longer composition. And I believe for longer composition, a simple linear model won't work. We have to build hierarchies. So recently, there's some very good work, Jukebox. They use hierarchical VQ-VAE, and I think that's a good approach. Yeah.
Yeah. I found that paper to be pretty interesting.
Yeah.
Do you think that, like, how far do you think we can get with this paradigm of larger and larger models and more data? I guess you already kind of commented on it, that we probably need something like hierarchy. We can't just have a larger flat model.
Yes. Yeah. We cannot just have a large flat model. That won't work. We have to build hierarchies. Yeah.
Yeah,
And
I see.
I believe that by building hierarchies and make the hierarchical representation at each level more interpretable, we can shrink the data sets dramatically. I guess the key is to impose the so-called good inductive bias, so that what the model learns is similar to what we human perceive. Yeah.
Hmm. I see.
Because how human perceive the world is, it's not the way. It's just one way. So we have to, in order to interact with the model, we have to kind of guarantee that when machine trying to understand the world, they should understand the world in a similar way that we human understand it. So, in order to achieve it, we have to impose some very strong inductive bias.
Right.
And
Yeah.
that will
Yeah.
come from using knowledge, I guess. Yeah.
Yeah. Because ultimately we want to create music that's sounding good to humans, not to the machines.
Yeah. I'm not sure what is the good music from a machine's perspective.
Yeah. Yeah. One more question on this. It's kind of a
Philosophical.
difficult, yeah. So in the game of Go, right, we had this AlphaGo moment
Yeah.
where we really knew that computers had reached the superhuman level in Go.
Yeah.
What do you think, in your perspective, could you come up with an equivalent thing for this music generation? Like, when would you know that we've gotten to the point where we're able to generate really good music with these types of models?
Well, human can decide it, right?
Hmm.
Because we're listeners and we'll say, oh, that's even better than Beethoven. Maybe one day we can achieve it.
Right.
But I would say music AI is, or in general, creative arts, underlying is very different from trying to solve a autonomous driving car problem or goal. And
Hmm.
I told the story to my student that let's imagine in a future city, 100 years later, in a future city, that there's only machine, no human. So what activity we could imagine happening to that city? So obviously, there are autonomous driving vehicles, right? Because they're machines that are trying to optimize their time and energy. And they could even play some game like Go, because that's a very good way to test whose algorithm is better when dealing with uncertainties, right?
Mm-hmm.
But can you imagine two machines play music? Or what? I can't imagine that. It just doesn't make sense to me. Because the underlying problem is music is a media. Sorry, music is a medium. Yeah. It's not an object. If we are talking about objects, then AI will certainly become human, and human are of no use. But if we are talking about media, then human is always there, because the definition of music is, it comes from human, and it will ultimately go back and serve human.
Yeah, if you could imagine having somehow restarting humanity multiple times, I would probably expect that after a while, the humans would invent all of the different instances of humanity would invent music. But maybe the same thing wouldn't be true, like you're saying, for machines. Yeah, so there's something there.
Yeah.
Maybe we'll go on to the next topic that you went into, which is this improvisation.
Mm-hmm.
So how would this be different from accompaniment? I guess because maybe part of an accompaniment could be that you have some improvisation.
Oh, yes. Improvisation is just the score is not 100% predefined. For expressive performance, your degree of freedom is your timing and dynamics, and for improvisation, you have some more freedom. Yeah, but you still have to play in the tempo, in the beat, and sort of in the chord. But what are the detailed pitches? You can decide it.
In terms of what you looked at here, or what the state of the art was, what type of improvisation were you dealing with here? Was it like a full jazz solo, or what did improvisation mean in this thesis?
In a thesis, it just means folk song improvisational accompaniment.
Mm-hmm.
And in my thesis, I did it in a very naive way. That it's a unit selection algorithm, sort of. So it's not a it's not really generating the accompaniment. It's doing unit selection. Yeah.
I see. Yeah. But this also seems like it's still a very difficult problem.
Yeah, but now I'm doing it using VAE and sample from the latent space, so that we can truly create, the accompaniment actually on the fly, and we can say to control the accompaniment by chord, pitch contour, and rhythm pattern. We can do it now. Yeah.
If I walk into a jazz club, how far are we from having a machine learning system be one of the players? I'm guessing pretty far.
Pretty far away, because jazz is the most difficult topic. Jazz is just too hard. It's very difficult. But I would say for popular song, maybe we're just several years away, 3 to 4, I guess. Maybe I'm very optimistic.
We're making progress on some problems, and some are still very far away.
Yeah. Maybe by the time you graduate, we can have a pretty decent, pop song accompaniment system. Yeah.
I see.
And
they could play the graduation ceremony song.
Yeah, and it all relies on the so-called hierarchical model. As long as we can build a good hierarchical representation, I guess 3 levels of hierarchy is enough for a pop song. we may need a couple more for symphonies, sonatas, but that's future work. Yeah.
Intuitively, what would the three levels represent for a pop song?
Motive, phrase, and the song.
Okay, and then maybe we'll go on to the third, at least the way I saw it, like the third kind of topic that you addressed in your thesis, which was the robotics. So getting robots to have these gestural and facial expressions. Could you just talk a bit about how you got interested in this and what the problem is?
It's just purely an accident. I flew to Japan. I forgot why I flew to Japan, but just before I flew to Japan, I saw a YouTube video and Wasida's robot. I said, "Wow, that's fascinating." I've never seen any music robot, but now we have a lot of music robots around the world. But by that time, I guess it's just Italy and Japan. And I should have emailed to them, say, can I visit your lab? And they say, yes. And I just visit them. And actually, when I visit them, the robot is kind of not working properly. And it's summer vacation. So only one undergrad intern and a master student was around. So we work really hard for several days to fix it, and eventually it worked. Yeah,
I see.
Work out. So I actually did minimum of programming. It's just because the robot is purely driven by MIDI messages. So I only have to set up some rule-based methods saying that if I'm speeding up, if I'm slowing down, if I'm doing such and such, what should be the facial and gestural expressions, and plus some randomness. Yeah.
I see. So again, it seems like here you kind of set up this almost like a baseline, and then you can build off of it to try to do more sophisticated things with the robots, like something more sophisticated than the rule-based methods.
Yes, and the reason why I'm interested in it is I think musical expression is not limited to timing and dynamics. Now I should say it's multimodal. Yeah, because now I'm working on multimodal representation learning. And at that time, I'm not thinking of this, but I just have the intuition, the gut feeling that musical expression is very, it's not just for sound. It's a global thing. Yeah.
When I was an undergrad, I was in Philadelphia, and they had this pass for students where we could go and sit right at the front of the orchestra for like $5. So I actually went to a few of the shows, and it does seem like there's an added aspect to seeing it live where you're seeing how the person's kind of moving with the music. It's different than just listening to the music itself.
Oh, it's very different, and sitting large crowd will kind of twist your perception somehow. Yeah. Because I'm a performer, and I know that I will get super excited when I see 500 audience. And there is a weird feedback loop between my performance and, I would say, the breadth of the whole hall, all the audience, all the people. Yeah, it feels very different or unique. It's a unique experience to use your music to guide the breathing of 500 people.
That is interesting. And I guess it goes back to this idea of the difference between a musical score and the actual performance. So it's so difficult that it gets to the point where the performance is actually going to depend on the number of people in the crowd, potentially.
Yes. And also goes back to the behavior leads to representation, and representation come back to guide the behavior loop. Yeah.
Those are kind of the three major things that you looked into your thesis. And I guess we've talked a bit about this work in generation. What are some other things that you're looking into now? And maybe talk a little bit about the lab that you're building at NYU Shanghai.
Yeah, the lab is called Music X Lab.
Hmm.
And I built it in 2017, shortly after I came to NYU Shanghai. There are several groups. The first group is the largest group is the automatic music generation group. So the composition thing that we just talked about. And there are two undergrads actually working on automatic accompaniment. So that's the second group. And now I'm trying to build a voice following system. So not I play electronic piano or play the electronic flute. So because humans, we can sing out of tune, and how we can do accompaniment when we are singing out of tune that's a pretty hard problem. Yes. And there's also a group, pretty big. It's called multimodal music learning group. It's computer-aided instrument learning. So so far we're working on computer-aided flute learning system. Yeah. So we have a hardware that we have a hardware that's which can lead you to learn the music purely by muscle memory. So we have a flute, and the flute is equipped with finger rings that are driven by the motors, and the motors are of course controlled by the computer program. So you just insert your fingers into these finger rings, and it just moves your finger. And when it moves your finger, you just learn the music by feeding it.
I see. Yeah. And then is there a machine learning problem here? So trying to create a model of the student or something, or?
Yes. And there's something called adaptive learning. And the idea is to, in a real time, detect how good you are. And if you are making a lot of mistake, then the finger rings will change your behavior. But if you are doing good, they will just leave you free. So it's kind of, teacher forcing and schedule sampling applied to human.
I see.
Yeah, and it works pretty good. We can speed up the learning process by 3 times.
Oh, wow.
Yeah. It's very effective.
So you're saying if someone's learning a new piece, you could actually measure that their learning time is decreased?
Yes. If you have to spend an hour, now we can do, less than half an hour or 20 minutes.
Yeah, that's fascinating. Do you think this could be applied to pianos as well?
I had a prototype in my head, and I drew it one day. But my student complained that it's too big, and we do not have that big, 3D printer.
I see.
Actually,
we had a 3D printer for your ideas.
I do have a 3D printer in my lab, but it's pretty small, so it's only for flute. Actually, 2 of my students were attending, and they have a workspace there, and they are just about to build a prototype actually, but sadly the pandemic stopped everything.
Yeah, because I used to play piano, and the place that I learned piano, they used a lot of these Roland pianos, which are electronic, and they would just have the MIDI file playing in the background, and you'd kind of play along with it. So it seems like there's a lot of room there for introducing some type of machine learning.
Yes. And now the group is trying to not only learn some particular pieces, which most music AI algorithm was trying to do. We're trying to learn the inner musicality of how to read music, something like this. Yeah, how to read music and perform, or the so-called the side playing technique. Yeah.
And then in terms of machine learning topics, what are some of the methods that you've been using?
I'm not sure. Maybe reinforcement learning.
I see.
Yeah. For that project, I mainly applying deep learning algorithms to human, actually.
I see. And then one last thing that I saw on the website, which I'd never heard of before, there's something about slime
I
molds
know.
and music.
Yeah, that's one of the craziest thing I've ever done. It's not very common for deep learning or machine learning guy to work on hardware and biology. I should thank to my postdoc advisor, Michael Casey and Xingdong Yang at Dartmouth. So I get a so-called Newcomb Fellowship, and it's very open. It's just saying that I give you some money, you can do whatever you want. And since at that time I already got the offer from NYU Shanghai, I'm saying that, oh, maybe I should stop my, just stop a minute for my machine learning and performance research. I should think of something different, something that I wish I could be doing during my PhD, but do not have the bandwidth. And so the computer-aided music education project purely comes from a bar chat with Xingdong Yang, and he told me that, Gus, you can build a system for professional musicians, but I just want to learn to play a simple song on the flute. Can you help me? So that's where that project come from. And speaking of the slime mode, is one day I went to a talk, and the talk is saying that slime mode is a single cell creature that has much intelligence. It can solve maze, and and it can memorize. It has very good memorization on timing. So there's experiment, very fun experiment, that the slime mode do not like cold air. So if you expose it to cold air, it will stop growing, stop moving. And then it's hot, it will start growing again. So 30 minutes freezing, it will stop, and 30 minutes remove the cold air, it will start to grow again. So you repeat this process for several cycles, and then suddenly, even if you do not present it with cold air, it will still stop moving. And this can last for several cycles. So this to me is supervised learning already. So I'm thinking that, oh, if this live creature can do supervised learning, can I just manipulate the input output and let it do genre classification, or even play the music?
Wow.
So I did the experiment. I calculated some slime mode in my computer music lab in Dartmouth. and people say, yes, you can do it. You imagine that.
What have you got the slime mold to do so far? Like, where is the project at?
Well, it's moving really slowly, and we are still trying to associate, trying to find the good stimulus. Eventually, I want to be able to perceive music and do genre classification, but now we're still at a stage of trying to find a good stimulus that could be recognized by the slime mold. So for example, for our human, our auditory perception is from 20 hertz to 20,000 hertz. Anything beyond this frequency range, we cannot perceive it. And so for slime mode, it's gonna be the same thing. It has its own calibration. It has its own hyperparameters, and we have to do experiments to figure this out. We're still, at this stage. Yeah, that project is moving really slowly. Yeah,
it's fascinating though, and I like the backstory of this. It started with a kind of call for very open-ended research, and you ended up on this direction with slime molds. It's fascinating. So maybe to end, do you have any advice for someone who is maybe in a similar situation that you're in. So they're maybe really interested in music and want to get involved in this idea of combining music with artificial intelligence. Where could they maybe get started?
That's a very good question. Actually, most of the students I'm currently advising, they got a way better background than I was when I was in my undergrad.
Mm.
Yeah. So because nowadays students know deep learning, machine learning, even in their freshman year. I don't know. Maybe the advice is for your undergrad time, try to enjoy your passion. Do not think of graduate school that much. Just do whatever you love to do. If you love music, try to be a good performer, try to be a good composer, because once you really start your PhD work, you do not have that much time to to really cultivate your musicality. Yeah, be a good programmer, be good at math, be good at music. That will set up your foundation. Yeah, and then in a graduate level, you can start to merge this expertise. But if you do not have the raw material, there's nothing to grow. Yeah.
Yeah, yeah. And I think you started by saying that all of the problems or most of the problems in machine learning for music are driven by the music itself. So it's good to have that experience with the music itself.
Yes. Yeah.
Yeah. Okay, well, thanks so much for giving up all
No
the
problem.
time for this interview.
Thanks for
And
having me.
yeah, it was great going back and reading what you worked on and seeing how it connects with things that you work on today. So thanks.
Yeah, and it's great to connect these things on the fly when you ask me, and it's sometimes. I mean, many of the stuff I've never thought of before, but when you ask me, yeah, there's an underlying outline.
Mhm.
Yeah, thank you.